So now we have learned a little bit about spectra. We know their basic properties. We know that every set in the complex plane that is bounded, closed, and non-empty could be the spectrum of some operator. And we know how to compute the spectra of convolution operators and even of periodic operators. Nevertheless, computing spectra is in general very complicated matter, and that's why we should come to a section that's called approximation of spectra. Well, in chapters 3 and 4 we have learned how to approximately solve the first two problems of linear algebra: linear equations and linear least squares problems. In both cases, projection methods did a good job. Now comes the third problem of linear algebra, eigenvalue or spectral problems. But we already saw, like in the last section or in section 3.2, that already for very simple examples such as the forward shift, where the spectrum is just a unit circle, at least if you take the forward shift over the integers, so the bi-infinite matrix, the spectrum may be very poorly approximated, well, actually not at all, by the spectra of its finite sections. So for the forward shift, on the one hand we have the unit circle, and on the other hand there is just the origin. And no matter how large you make your n here, the spectrum is always going to be just the point, the set consisting of the point 0. And unfortunately, this is what typically happens. Strong convergence of AN to A does not imply convergence of the spectra in whatever sense. And actually the situation is even worse. Also, uniform convergence does not generally imply convergence of the spectra. And this is unbelievably bad news, so we should see this in at least one example. Look at this operator sequence. You take the two-sided infinite forward shift, but you change one single entry, which is this one, into 1 over n. And then as n goes to infinity, the only thing that's changing is this little entry, and that's changing into a 0. And of course that's uniform convergence, because if you look at the difference of the two, then the difference is going to be an infinite matrix that only lives in one single entry. So the norm of that difference matrix is just the size of that one entry, and that goes to 0. But for every n you can find the similarity transform that brings your matrix AN to the forward shift. It just means you can find an invertible operator such that if you multiply it from the right and its inverse from the left to AN, then you always get the forward shift, and you can compute it by hand what that is. It means that the spectrum of AN is the same as the spectrum of the forward shift, which is still the unit circle. And now we have to look at the spectrum of A. And because we have this 0 here, your operator A, or your infinite matrix A, decouples into a block that's sitting down here and another block that's sitting down there, and it becomes block diagonal. And that's why the spectrum of A is just the union of the spectra of this and that block. But these two green blocks are essentially the same. You can just transform one into the other by a simple flipping around the axis. It's just like a reflection on that line. And this is now the one-sided shift. And we know it's not invertible. I mean, you can see it has a row of zeros. It's not surjective. Which means 0 is in the spectrum, and it's far away from these spectra here. And in fact, the spectrum of this one-sided shift is the filled unit disk, of course including the boundary because spectra are closed. So the spectrum of AN is constant. It doesn't change when you change n. It just stays like this. And then as n goes to infinity, or you could say as that entry jumps to 0, the spectrum jumps. It immediately jumps to that filled unit circle. And I mean, you could try whatever you can. You would not be able to call that convergence. And I mean, that example is just taking you any illusions to ever approximate the spectrum of your operator, if not even uniform or norm convergence is strong enough to do the job. So we could just stop here and go home deeply depressed. Of course, we shouldn't do that, so let's give some positive results here. And there's even more than one, so let's enumerate them. The situation is better, let's not quantify how much better, but it's not so bad for self-adjoint sequences. So when AN equals AN star and goes strongly to A, which will then also be equal to A star, ask yourself or ask me why this is so. Then one can show that every point in the spectrum of A can be approximated by points from the spectra of AN. And note that even strong convergence is enough for that statement. As a consequence, the situation is better when you're interested in singular values rather than spectral values, because singular values are the square roots of spectral values of A star A, which is self-adjoint. Here's another positive result. Sometimes periodization helps. And we saw that in section 3.2 for the forward shift, and we will now show it for all convolution operators, but it actually holds for larger classes of operators. But let me first show what it is. So for illustration, let's take a convolution operator, even though we now know that the spectrum of a convolution operator can be easily computed. So there's no need for approximation techniques. And the trick is to express that operator in terms of the forward shift. Well, the forward shift has its ones here on the first subdiagonal. So this is A1 times the forward shift. And well, okay, you could write the identity, which has its ones here, as forward shift to the power of 0. So you have A0 times that. And then the backward shift, which is the inverse of the forward shift, has its ones here. So you have A minus 1 times that. And the square of the forward shift would move every sequence just 2 positions forward. So that would have its ones on the second subdiagonal, which is where A2 is sitting, and so on. And we recognize that term here, only that where now the forward shift capital F is sitting, there used to be a little t, and then we called it A upside down hat of t. So now this is A upside down hat of F. Okay, to show you what we mean by periodization, I should better go down to an example of this class of examples. So this bi-infinite three-diagonal matrix can be written as minus 2 times the backward shift, which is the inverse of the forward shift, plus 5 times the identity, plus once the forward shift. Now if you pass to the FSM, you get this sequence of n by n matrices here. And then in section 3.2, we discussed, for the example of the forward shift itself, that it seems a good idea to periodize this in the following way. You take the minus 2 that used to sit here but was cut off at the top, and bring it back in at the bottom. And similarly, the one that used to sit down here but was cut off by this truncation is now coming back in from the top. And now the cool thing is that you can express this new periodized finite section matrix in a similar style as we did here. You just have to exchange F for something else. And let me denote that mysterious matrix by Rn, because it depends on n, and R is for rotation. Well, let's see. We have this 1 here, and the 1 Rn should come from the following entries, which are just those matrix entries where you see a 1 here and here. So similarly, this part of the matrix here, which is carrying the -2's, must stand for that expression. Okay, and then finally the part that carries the 5's comes from this bit. Okay, and it's not difficult to see that all this is coming true if you take Rn to be the following matrix. It's exactly the matrix that we marked in red here and multiplied by 1. Okay, and then its inverse, it's transpose, and that's what you mark in green here, and then multiply by 2. And its 0th power is just the identity, and that times 5 gives you the blue bit. If you take higher powers like to the power 2 or 3, then you get something that we observed before. I mean, what is this matrix doing to a vector? It's just like the forward shift. So it's shifting everything one position down, but the entry that's falling out at the bottom is coming back in from the top. And we did exactly this operation in an example that fixed the problem for the forward shift. And now let's see whether this can fix the problem for all convolution operators, and of course it's going to do so. By the way, if you tried to do the same up here with your usual finite section AN, then instead of this Rn here, you would have to use a matrix Fn that gives you just these ones. But then that's not invertible. So it didn't inherit the invertibility from the infinite matrix that it comes from, which is the bi-infinite forward shift. And of course that gives you problems when you want to write down things like this. So this is not possible. Okay, but now let's see what the spectrum of the periodized finite section has to do with the spectrum of the original A. And let's come back to the general setting here. We have written our infinite matrix, the convolution operator, as the A upside down hat function applied to the forward shift F. Okay, and just in the very same style, we can write our periodized finite section as the same function applied to this Rn. Recall, you can't just simply do that with the non-periodized finite section. Okay, how is that helping in computing spectra? Well, remember that the spectrum of the square of your operator A is just consisting of the squares of the spectral points of A. And even if you take a polynomial like 3 times A squared plus 2 times A minus 5 times A to the power of 3, and you're looking for the spectral values of that, you would just take the spectral values of A, plug them into the same polynomial, and that's your result. Okay, so that's what we're going to use now. And this is the key step here. So we just say that the spectrum of this matrix function or operator function is just the same function applied to the spectral values of this operator F forward shift. Okay, and now we can simply copy the same line down here, only with the other operator here. And then it remains to recall that the spectrum of the forward shift is just a unit circle. And by the way, here we derived, again, in a very elegant style, the formula for the spectrum of a convolution operator that we already derived in the last section via the Fourier transform. Right, so you just take your A upside down hat and apply it to every point of the unit circle, and the values that you get give you the spectral points of A. Okay, now what's the spectrum of Rn? The spectrum of this operator here, we did this already in section 3.2, just a little reminder. And the key idea was to ask yourself, what happens if I apply this operator n times? So n is just the size of the matrix, the length of the vector. And if you apply it once, then everything is moved one position downwards, and the data that falls out at the bottom comes back in at the top. If you do that operation n times, then every piece of data is back to the position where it used to be at the beginning. So that must mean that the nth power of my operator is just the identity. And therefore the eigenvalues of Rn, if you take them to the nth power, give you the eigenvalues of the identity, but these are all equal to 1. So the spectrum of Rn consists of the nth roots of unity. So for example, if n equals 12, then this just looks like the hours on your wall clock. And because there's always n of them and they sit so nicely on the unit circle, this set is often denoted by t, just like the unit circle, sub n. So now we know what to substitute in here. So while here you get the whole curve that is traced out by a upside down hat when t is running through the unit circle. Here you're sampling your unit circle in an equidistant way, and then you're looking what the function is doing with that subset. But it seems pretty clear that when you increase your n, then these dots become denser and denser on the unit circle, and thereby these dots should approximate the true answer better and better, unlike what you get when you're using non-periodized finite sections. Okay, so for convolution operators, this is all pretty clear, and you can prove it on one page. We are currently working together with a PhD student on generalizing this concept. Of course, you can do this trick with much more general matrices to see what we get. Then it looks promising. So the message is not all is lost when it comes to approximating the spectrum of your operator. Okay, so our first positive result was that for self-adjoint operators the situation looks a bit better, and then that implies that singular values can be approximated much better than spectral values. Then periodization is an idea, and here is a third comment, a much larger concept that can be used for the approximation of spectra, but also for some other things where spectra are inefficient or at least not quite sufficient, are so-called pseudo-spectra. And this is a topic on its own that deserves its own subsection.